we refresh aliphatic electrophilic reactions. Both benzene and alkenes are susceptible to electrophilic attack primarily because of the exposed pi electrons. Hello everyone, I am Dr. Zosimus Divya Lobo, Assistant Professor of Chemistry. Shall we learn about FTNMR, that is Fourier Transform Nuclear Magnetic Resonance Spectroscopy? We see the introduction of FTNMR spectra. The sample is irradiated with an intense peak of all radio frequencies in the desired range at once, while keeping the magnetic field constant. All the nuclei under study observe at the individual frequencies and are flipped to the higher energy spin states. This results in an interferogram called free induction decay or time domain spectrum. Time domain spectrum is converted into ordinary frequency domain spectrum by performing a mathematical operation known as Fourier transformation. This technique is called pulsed Fourier transform NMR spectroscopy. It gives a good spectra even with a very small quantities of sample. The principal advantage of FTNMR spectroscopy is a great increase in sensitivity per unit time of experiment. We see the theory. In a pulsed spectrometer, the sample is placed in the magnetic field and irradiated with a pulse of high power radio frequency energy with the frequency range sufficiently large to cover the entire range. This pulse simultaneously excites all of the nuclei in the sample. The excited nuclei begin to return to the ground state and radiate absorb energy. The detector collects this energy producing free induction decay, which is the sum of all nuclei radiating over time. The pulsed technique was developed largely in response to the need for much higher sensitivity in carbon-13 spectrometry. A sharp, powerful radio frequency pulse of center frequency mu1 applied along x-axis generator the entire desired frequency range. The magnetization signals are almost immediately detected after the pulse in the xy plane and collected by a computer over a period of time which is called acquisition period. The figure shows the effect of various pulse angles, theta and expected signal. If the theta is 90 degree, we get a positive signal. Or theta is 190 degree, we get a no signal, that is inert. And 270 degree, we get a negative signal. The signals collected represents the difference between the applied frequency mu1 and Larmor frequency of each proton. The FID are then Fourier transformer by a computer algorithm into the conventional NMR spectrum. This figure shows the rotation of signal in xy plane after 90 degree pulse. In the axis of y, we get a positive signal. In between that is x and y, we get a lesser positive signal. Then x-axis we get a no signal. Then that is negative angle, we get a negative signal, then lesser negative signal. Next, we see the instrumentation. The sample is placed in the probe, which contains a transmitter and receiver coil and spinners to spin in the tube about its vertical axis in order to average out field in the homogenerators. The schematic diagram of a Fourier transformer NMR spectrometer with a superconducting magnet. The tube spins at the right angles of the z-axis, which is horizontal, whereas in the superconducting magnet, the tube fits in the bore of the solenoid and spins about z-axis, which is vertical. The transmitter and receivers are coupled through the sample nuclei. Peak areas are measured by the electromagnetic integrator that traces a series of steps with a height proportional to the peak areas. A proton count from the integration is useful to determine or confirm molecular formula, detect hidden peaks, determine the sample purity, and do quantitative analysis. Peak positions are measured in the frequency unit from the reference peak. Next, we see the carbon-13 NMR. The possibility of carbon NMR appears surprising at a first glance because the most abundant carbon isotope of carbon-12 has no net nuclear spin. Hence, it does not exhibit NMR phenomena. The far less abundant carbon isotope of carbon-13 has a nuclear spin of positive and negative and is detachable by NMR. The principle of carbon-13 NMR is exactly similar to those of proton NMR spectroscopy. The gyrometric ratio of carbon-13 is about 1/4 that of the proton. Consequently, the resonance frequency of carbon-13 is also around 1/4. Thus, NMR of carbon-13 can be observed 15.1 MHz in the magnetic field of 40,092 Gauss, while the protons is observed at 60 MHz in the same field. Similar to that, proton magnetic resonance spectroscopy, tetramethylsilane TMS is also used in the carbon magnetic resonance spectroscopy as a common reference compound. The chemical shifts are usually expressed in dimensionless delta units. Carbon-13 chemical shifts ranges from 0 to 250 delta. Next, see the common modes of spectrometer operation, which provides different kinds of carbon-13 NMR spectra containing different structural information. These are proton noise decoupling, off-resonance decoupling, gated decoupling. First, see the proton noise decoupling. In this mode, all the protons in the molecule are decoupled from the carbons. This is done by irradiation of the sample with the noise decoupler at the H1 frequency, that is proton frequency, while observing the spectrum at the carbon-13 frequency. Off-resonance decoupling. The couplings due to protons directly attached to the carbon-13 atoms are observed, but other couplings are removed. Gated decoupling. The gated decoupling mode, the areas under each peak is directly proportional to the number of carbon atoms, causing that peaks. Next, we see what are the factors affecting the carbon-13 chemical shifts, namely alpha, beta, gamma effects, effect of substituents of alkanes, effect of hybridization of carbon. First, we see the effect of hybridization of carbon. The chemical shifts of carbon is very significantly affected by its hybridization state. sp3 hybridized carbon atoms unsubstituted by heteroatom absorb 0 to 60 ppm downfield. Like sp2 carbon in the range of 100 to 150 ppm downfield. And sp carbon absorbed in the range of 65 to 90 ppm downfield from TMS. Next we see the alpha beta gamma effect. There is an increase in chemical sets on going from primary to secondary, secondary to tertiary, tertiary to quaternary carbon atoms, and the average increase for hydrogen atom replaced in the range of 7 to 10 delta. This is illustrated in the figure by moving from methane to neopentane. The alpha beta position exhibits de-shielding effect, whereas gamma position shows shielding effect. That's why we're getting the negative to higher positive. In this case, neopentane contains no hydrogen. The methane contains higher number of hydrogens. The last factor is last factor affecting the chemical surface, effect of substituents on alkanes. Simple alkyl substitution has much larger effect on carbon-13 chemical surface as compared to that of the proton magnetic resonance surface. The approximate carbon-13 chemical surface for the carbon atoms of alkane derivatives may be calculated by properly applying in the increment given in the table. It is gamma increment, that is substituents present in the alpha position. It may be terminal or internal. Terminal position we get a higher positive values. Internal position we get a less number as compared to the terminal position. The beta terminal to alpha terminal, beta terminal, most of the compounds get a lesser positive charges. In the internal position of beta, internal position, we get a lesser substituent, value of delta values. Then gamma, we get a negative. That's why we told about the shielding effect. Hope you have learned about FTNMR and C30.